Okay, I will share my screen on that part where we ended. So this is the part where we ended. Um, okay. So if my memory serves me right, class, we ended with, this is our second to the last slide, last meeting, on transfer functions of liquid level system. And the transfer functions are relating head to changes in the volumetric flow rate. And then also it could be either, the transfer function could either be relating the volumetric flow rate through the linear resistance and the changes in the volumetric flow rate to the tank. And we ended with the transfer function of the liquid level system wherein we have a pump which has a constant flow as regulated by the pump and the mixing process. So for the mixing process, this time you are relating the changes in the concentration of the system inside the tank to changes in the concentration of the fluid that is entering the mixing chamber. So our tau for this system is equal to the volume of your system divided by the volumetric flow rate. So of course having the unit time. For this afternoon, we will continue with the transfer functions, the transfer function rather of two non-interacting tanks. So let me try if this could show. Can you still view it if I will use the slideshow? Can you view the two non-interacting tanks transfer function? Um, any reaction? Can you see it?
Yes, miss.
Oh, thank you. So this is our transfer function for two non-interacting tanks. The volumetric flow rate from the first tank is dispensed in the atmosphere and then is introduced into the succeeding tank, and that is the second tank. So in this case, you only have two transfer functions to multiply. So this is the transfer function of the first, and this is the transfer function of the second. So this transfer function relates the level of the liquid in tank 2 to changes in the volumetric flow rate to tank 1. So in here, we have the characteristic time constants of the two tanks, tau 1 and tau 2, written specifically if they're not equal. R sub 2, of course, is the linear resistance to flow in your volumetric flow rate from tank 2. Now, if you convert this to this transfer function in the form of volumetric flow rate from the second tank related to the changes in the volumetric flow rate to the first tank, and if the tanks are identical, then our transfer function would be similar to the transfer function of the thermometer, which is just being squared. So 1 over tau s plus 1. Still, in this case, your tau will be volume divided by volumetric flow rate. By the way, this is liquid level system. So your tau would be, can I ask somebody, what is our tau for a liquid level system? You can write on the chat box, what's your tau for a liquid level system? This is correct. So Eugene, thank you. So that would be the product of the cross-sectional area of the tank and the linear resistance to flow. The one I mentioned about a while ago about tau being V over Q is for the mixing system. So we're talking about here of liquid level systems that are said to be non-interactive. Okay, now we proceed. Now, if our transfer function this time, or if we talk about the transfer function of n systems that are said to be non-interacting. So the general way of presenting such would be this, wherein we are required to multiply the transfer function of the individual systems. So the K sub I here is the gain of each of your systems, I representing a particular gain in your non-interacting system. Yes, Giselle, it's not
Miss,
transitioning.
yes, miss. Para kapalangyapon, miss, sa tunan interacting accounts.
Okay, thank you. So I'll go back na lang to our slides. Okay, thank you, Giselle. So for transfer functions, again, going back to what I was mentioning, for n systems in general, so n could be 5, 3, 4, or even just 2. So we just multiply the individual transfer functions. So we have the gain of each of the system written in the numerator, and we have the tau s plus 1 in the denominator. That is if we want to get the overall transfer function of this and non-interacting systems. So this is how we do it. If we have two interacting systems, so this time we say that the second tank, let's say for example, is loading the first tank. So that's how we say it, not the other way around, that the first tank is loading the second. No, we don't use that term in process control, but rather it is the second tank that is loading the first, meaning the level of the liquid in the second tank is said to be affecting the response or the level of the liquid in the first tank. So since they are interacting, this is now the way we write the transfer function. This is already derived from our textbook. What appears in the numerator is the linear resistance to flow of your tank 2, and you have here the corresponding transfer function, the corresponding time constants of your two tanks, and then the area of the first multiplied to the linear resistance to flow of the second. So this is the form of our denominator. And by the way, having said that this is the form of our denominator class, if we have a third order system, one way of checking, but it's not yet sure and it's not certain yet that you're doing the right thing, but more or less you are on the right track, is that if we have two tanks in series, whether interacting or non-interacting, your transfer function for the overall, or rather for the overall transfer function of your system, the denominator of that should be second degree. If you have three tanks, it should be third degree, and so on and so forth. So it tells you more or less that you are deriving the correct overall transfer function of your system if the degree of your denominator is equal to the number of tanks that you have in your system. I remember that because when I did give a quiz, or was it part of the exam, where in the transfer function in itself is not correct for the system because the degree in the first place of the denominator is not equal to the number of tanks or elements in the system. So it has to be equal. So in this case, since we have two, so we have a second degree polynomial in our denominator. If we have three tanks, this should be third degree. Okay, so however, our book just simply want to illustrate the concept of the second order interacting system. That is why it's only limiting it to second order or a system that has two tanks. If it has three, then you know how complex is this. If we are to go back to the individual material balances, then the process would even be more lengthy. It will take more time. Okay, now I will proceed. Now, for two interacting first order systems, the first transfer function that you saw here relates level to changes in the volumetric flow rate to the first tank in your system. This one, the other transfer function here, relates the volumetric flow rate from the last tank. This should be class Q sub 2 of S, not Q sub S of S. Q sub 2 of S over Q of S. So this is the volumetric flow rate from the last tank, the second tank, in relation to changes in the volumetric flow rate to the first. And this is your transfer function. However, this will only work if your tanks are said to be identical. And that is the, of course, the area, the cross-sectional areas are equal. If the cross-sectional areas are not equal, then we really have to go back to our material balances and of course check whether it's still comparable to this overall transfer function. I'm sure it would not be comparable to this anymore. Okay, so this is the limitation of this pre-derived transfer function. Now, generally, for a second order system, you have this form when especially the terms related to the response of a second order to a step input. When we talk about that, the form of your transfer function is something like this. Now, you have tau squared s squared in the denominator. You have in the middle term or in the second term 2 zeta tau s, and then the last term is 1. Why am I emphasizing this again? Because this is very important in determining the correct response equation to use, especially if we are dealing with a second order system that we need to know prior the value of the zeta. Because for different values of the zeta, we have a different response for a step input, if you can recall. So we have the underdamped response, we have the critically damped response, and the overdamped response. So we need to establish first the zeta. How do we establish the zeta? Of course, together with the tau, we make sure that the form of the denominator is written in this manner. So your constant here in the last term, in your third term, should be 1. If it's not 1, then simply divide your denominator and of course your numerator by that same constant. That way it will conform to this form. Then equate, if you can recall, you equate the coefficient of s squared to tau squared. And once you know already the tau, you substitute it here in the second term so that you'll be able to get the zeta. Because the coefficient here in your second term now will be equated to 2 zeta tau. So first determine tau and then determine the zeta. That's how we do it. That way we will know the correct or the appropriate response equation. Now, for the concept of the transportation log, this is common when, of course, I think majority of the industrial processes have equipments connected in the form of pipes. So if fluids are transported through these pipes, then this particular transportation log exists. And it's the only transfer function that is introduced in the introductory portion of process control that is not rational in form. So it is exponential. You could see here exponential, and your tau here is generally written as any constant. So any constant that appears with the s in your exponential function is the tau. Why am I saying that? Again, I remember that when you were asked to give, I think, informations related to the response of a particular system wherein you need to use the Taylor approximation, like everybody in the class, I think, probably an exception of 1 or 2 students, use the Taylor approximation. What they did is they directly made use of this equation without having to use the Taylor approximation. This Taylor approximation can replace this transportation log transfer function, especially if you're dealing with systems or equipments that are adjacent. So if you're going to write down the overall transfer function, that way you can come up with the response, the overall response of your system, accounting for transportation lag, you will have all expressions in the form of fractions. That is why we have this Taylor series approximation. Now, that's also together with this first order Padet and the second order Padet approximation. But this one is complicated, this one also. But the Taylor series is simple. It's the simplest of the three. So it can replace this one in here. how would you know the tau that you will place in here in the denominator? That would simply be the constant. That would simply be the constant that appears in the exponent here of your exponential function together with the s. So let's say, for example, this is e raised to negative 2s, so this should be 2. The majority did not use the Taylor's approximation. They went directly to the response equation without considering the approximation, which is dictated as instructed in the problem that you are to use Taylor's approximation. So be very careful with such instructions. So if you fail to follow the instruction, of course, even though theoretically or conceptually you're doing the right thing, but since you did not approximate, then what you're doing is entirely wrong. Okay, so how do you get the tau again? That's the constant that appears together with the s in the exponent of your exponential function in the original transportation log expression. So this is your transportation log expression. Now you have this first order approximation by Padet. First order in the sense that s is raised to 1, both in the numerator and in the denominator. Or shall we say your numerator and your denominator are both first degree. So that is why first order. Second order in here because your s here now has an exponent equal to 2. So you have these 3 different approximations to choose from whenever you wish to substitute any of the 3 approximation to the original transportation log expression. Because if you recall our discussion of this last semester, if you will not use any of this approximation, you will again go back to the concept of the second shifting property of Laplace, wherein after you have converted, after you have inverted your final function of S expression, you have to follow the 3-step procedure of converting it into the correct function of t. Now taking into account the e raised to minus as, where this time the a is the tau, and that would be cumbersome, rather than having to replace it with this expression, wherein all you only need to do is, of course, use the method of partial fractions without having to think back of what is the 3-step procedure in the inversion using the second shifting property of Laplace. That would also incur time. Okay, so that's regarding the transportation log. Now, if our system needs to be linearized, and what was discussed in detail in our reference book is the liquid level system, which needed to be linearized. So that's the only thing that they also place in here, although we don't limit it only to such systems. So if you notice, there was an assignment given on linearization for a thermocouple that measures the thermometer inside the furnace. And there was also an assignment on the linearization needed for a kinetic equation, an equation that you have encountered already in your kinetics. So we don't limit the linearization procedure to these systems only. When your system is not already modeled using a first order differential equation, there is a need for you to linearize. There is a need for you to linearize because we can only derive the transfer function of any system for a first order differential equation. If it's not linear, for a linear differential equation, if it's not linear, you need to have it linearized. So for this particular system, a liquid level system, wherein the relationship between head to volumetric flow rate through the linear resistance is not linear, you have this pre-derived linearized transfer function for it. The R1, which is the gain now, that is written in the numerator of the transfer function, is the Actually, it's just this constants here. 2 square root of h sub s, that is the steady state level of the liquid inside the tank, divided by a constant c, which is a characteristic or is related to the characteristic of your resistance. It's not linear, so we take away the word linear, of your linear resistance to flow. In this case, your tau would still be AR, but your R here will be this. So a function already of the liquid level and the constant of your resistance to flow. Your Q sub O, the volumetric flow rate through the resistance, is C square root of H. So you could see now that when you place this in your material balance equation, you will have a problem with the H because it has an exponent of 1/2. And as such, there's a need for you to linearize. So I suggest that you just familiarize yourself with this equation, with this formula. That way that you won't need anymore to linearize when the need arises. Okay, that's for the liquid level system. Now also, we've covered controllers. Let me check. So I jump to that. We also covered valves. So after linearization, we have the valves. In here, we have a control valve, which is comparable to a valve which is regulating the flow of the liquid through the pressure in which, to the pressure that is applied on its top portion. And we have this particular valve discussed wherein you have a diaphragm that goes up and down due to the pressure that is applied to the top part of this particular valve. So for a control valve class, the transfer function relating the changes in the volumetric flow rate through the valve and the changes in the pressure on the top pressure of the valve is this. So it's the steady state gain, K sub B. So we place the subscript B to represent that that's the steady state gain of the valve, divided by tau V may S pa na di plus S plus 1. So the denominator is comparable to that of the thermometer or first order system, tau sub Vs plus 1. So this K sub B that you see on top, which is the steady state gain, is also a constant of proportionality between the steady state flow rate, Q sub S, and the valve top pressure, P, or the pressure in which your valve is subjected to. And tau sub V is the time constant of the valve. Now, for many practical systems that are using this control valve, this tau sub V is very small, that if this is very small compared to this one value here, it's like its value is not affecting 1. So it's just like you have 1 in here. So in that sense, you simply have 1 in the denominator. So your transfer function then is even simplified in this form for your control valve. So you have Q of S over P of S equal to K sub V. Now, if this control valve is together with a first order system where there is no interaction between the valve and the system, we can write its block diagram in this form. So I'd like to go first to the block diagram because it could be easily deduced. I'm referring to the transfer function if the block diagram is written. So your valve here, the valve transfer function, is worked on by pressure, the top pressure or the pressure on top of the valve. And the output of your system, the process here, is Y. So based on the concept of the superposition of the plus of the transfer functions, if you want to determine the overall transfer function of this system, all you have to do is multiply the individual transfer functions. So if you, let's say, for example, in this case, you only have 2, then you multiply their transfer functions. If you have 3 blocks here, then you multiply as well the transfer functions inside each of the blocks. Your output would be the last variable you see, and of course the input will be the first variable that you see entering the first block. So in this case, the overall transfer function of your linear valve and your first order system in series with no interaction is the one that you are seeing here on top. Notice that the transfer function of the valve is the original one, wherein we haven't assumed that tau sub v is very small. Okay, so this is the original transfer function of your valve. If the pressure, the top pressure on your valve changes in the form of a unit step function, or there's a unit step change in the pressure, then your y would be, of course, this one, wherein you already replace the P of S by 1 over S and cross-multiplied it to the overall transfer function of your system. If we do the mathematics upon inversion, this will be the response. Okay? The overall response for your process and valve system. If your tau sub v is a lot smaller than the tau sub p, tau sub p is the time constant of your process, yes, this y sub t response would be something like this. Primarily, class, if you look at it, why would it be simplified into this form? It's because if your tau sub p is a lot greater than tau sub v, or tau sub v is a lot smaller than tau sub p, in terms of value, the value of this will be very small compared to this. Very small in the sense that this one is very big. So it's just like this is nowhere, more or less 0 compared to the value of this. So you have 1 minus minus, so this becomes plus already, because more or less this becomes 0. And this tau sub v and tau sub v here will just cancel each other. This one here is very small compared to tau sub p, so it's just like it's not there. So it's just like you have tau sub p and tau sub p, which will also cancel each other. So the response will then be something like this: 1 minus, so you already have plus and plus, but you have here minus. So 1 minus, this is the thing that is left, e raised to negative t over tau p. Now, this response is actually comparable to if this particular part of the transfer function of your valve will not place there in the first place. So if you simply multiply the transfer function of your process with k sub v, which is the simplified transfer function of your linear valve, so amo na lang siya ang 1. So amo na lang siya ang mag-1. So if you're going to have this inverted, actually this is the response equation. So whether you go to the original, and from the original transfer function simplify, if tau sub v is lesser than tau sub p, you still get the same response if you already go, if compared to simplifying it first, where the transfer function of the valve is already only written as k sub v. So the same response equation results from that. So this is now the transfer function for your process and your linear control valve when your tau sub v is a lot lesser than tau sub p. So this is your transfer function and this is your response for your system. Okay, that's regarding the transfer function of the final control element, which is the control valve. Now, in terms of the transfer function of controllers, we go now to the controllers. We're done with the process. So the process could be liquid level, thermometer, mixing, could be even reactors, stir tank heater. Depends on what the problem gives you as your process. We're done with the final control element. Now we go to the controllers, the ideal transfer function of controllers. Now their transfer functions are dependent on the type of controller. So we have proportional controller, we have proportional integral controller, we have proportional derivative controller, and we have the PID, the combination of the three. So for the proportional controller, it produces an output signal that is proportional to the error. So this P sub S actually is written here. It's P minus P sub S, meaning the change in the pressure is equal to K sub C times the error, where K sub C is the transfer function of your controller. The E is the error. So it's explained in here. The K sub C is the gain or the sensitivity. Now, for a proportional controller, it's as simple as this. And from here, as I've said, you can write the P minus P sub S on the left side, and you have K sub C error on the right, and you will have here capital now deviation P of S over epsilon of S equal to K sub C if you transfer it here. Now taking the Laplace of the deviation of these two. Now that's the transfer function that you see here on the next slide for the proportional controller. Okay, so this is the transfer function for your proportional controller. This is the starting point where this is the original type of controller, and from this they modified it to make it even perform better than the original. So we have from the proportional controller, we have the proportional integral controller. So from the original, you added the reciprocal of the time integral. So this is the time integral here, the tau sub I. This is the tau sub I, the time integral. The reciprocal of that is what we call as the reset rate. So this is the original. You just added the 1 over tau sub IS. This is the transfer function of our proportional integral controller. Now, we also have the proportional derivative control. This one is PI, this one is just P, and this one is PD. So it adds to the proportional action term K sub CE, another term that is proportional to the derivative of the error. So the derivative of the error, or the time derivative of the error, specifically is this. So aside from this one, which is just part of your proportional controller, then without this, it's just proportional controller, you accounted for the derivative of the error. Now, terms related to this are the rate control or the anticipatory control, and can be used to represent the same PD controller that we are referring to. The effect of the derivative action here is to anticipate the linear change in the error. So there is anticipation on how the error will behave over time. Okay, so this is PD controller. The further modification is the PID controller. So this time you don't only account for that derivative of the error, but you account for its integral or the time integral of the error. This is the error here. Okay? So a combination of proportional, integral, and derivative control. And in that sense now, if we have this only for PD, then we add another one if we have PID. So we have this tatlo na din sila. If it's just proportional, that's the only transfer function you see. So the transfer function now for the PID, the most superior of course of the three, if you're going to add on off, then of the four, this is now its transfer function. Okay, it accounts for the time derivative and the integral of the time integral of the error. Okay, so this is the derivative time, the tau d. This is the integral time. Okay, as defined and discussed to you as well. Okay, now we have the easiest part. Second easiest part in controls is in the analysis of the block diagram. How we write the overall transfer function, or how we write the equation relating the output or outputs, depending on how many outputs we have, to the changes in the input for our system. So it's very easy. Inside the block, you have the transfer function, And what is pointing to the black is the input. And it said that your input is working on your transfer function to bring about the output. So the output of these two enters the summing junction. So the summing junction determines the sign of the product of these two, and the corresponding resulting sum of the product here, the sum of the products of these two will bring about the uh, controlled variable. In this case, it's the t prime of s. So as you can see, we just multiply the input to the transfer function, the input to the transfer function. In this case, class, we have two. We have one output only, but we have two inputs. Okay. So an output related to two different inputs. So one may not have any change, the other may be changing, or it could be that both is changing. So if both is changing, then we can't have a transfer function. Because when we speak of a transfer function, it's just relating one variable to another. So not two variables to another. So this is for our process for a steered tank heater. This is just an example, the same example given to you the previous semester. It could also be simplified in this manner, wherein if it's written in this form, class, this is the overall transfer function of your system. Okay, this is the overall transfer function of your system. And your Q sub S is being multiplied to the product of T sub I prime of S with WC. So actually, this was just simplified. This equation was just simplified where you factored out 1 over WC over tau S plus 1 from the two terms here. So bringing about this equation. Okay? This is another way of presenting the process. Now for the steered tank heater, this is our simple representation for the measuring element. The difference between tau prime of S and tau prime sub M of S is that the actual measured value coming from the measuring element is not actually the actual output of your steered tank heater. So there is lagging already because of your measuring element having its own time constant. So it's tau sub M. So it's not instantaneous. So it's not right away the same value that is being received by your measuring element, that it's not the same value that your measuring element sends to the controller. So it's just the T sub M, not the T. Now for the controller and the final control element lumped into one, so the set point is being compared to the sense value, then the difference is the error. The error is where your controller is acting on. So the error is where your controller is acting on. That way it can actuate your final control element on the flow regarding the amount of heat that will be supplied to your steer tank heater. May it be in the form of the flow of the heating medium or the current that is supplied to your electrical heating device. So that would be it. So the controller is working on the error and then actuates your final control element on what should be the Q of S. So your transfer function for your final control element should be taken from this class. Just transfer the E of S here. So that would be the transfer function of your controller already. The error here is taken from the comparator, which compares the sense value to the set value. Okay? Now, if you're going to lump or if you're going to place all the blocks in one block diagram for your steered tank heater system, this would be it. So this is your process. So the modified one was reflected here. This is your controller. This is your sensing device. That's for the block diagram analysis. Actually, you are given much more complicated blocks to analyze compared to this. This one is just a very simple sample. Now for the route test, this is where we ended. We test whether our system would be stable if subjected to a certain disturbance in the input. So in here, we work on the characteristic equation, which is just the sum of your transfer function and 1 equated to 0. It's 1 plus g of s equal to 0. Now we simplify that particular equation, that way it would be in polynomial form. So once any of the terms in that particular polynomial is negative, there's no need for you to do the rough test or do any test whatsoever, because right away you can conclude that your system will be unstable. However, if that particular polynomial equation has all the terms positive, there's still a need for you to validate that. So how to validate is you do the route test. Doing the route test is, of course, requiring you to do, or rather to make this route array. So this A's here are the coefficient actually of your polynomial equation taken from your characteristic equation. So the first term there has the coefficient A sub O or A sub 0. So you place here the coefficients that have the even subscripts and top, then the odd subscripts will be written at the bottom. And then determining the B1, the B sub 2, the C1, and the C sub 2 is comparable to your how you process your determinants, then more or less in that same format. Going up is positive product, that is going down is negative, and then you divide it by this, it brings about this one. If it's B2, it's the same as this one, but this one going up and this one going down, and you divide it by this one, so you have B2. Kindly check. I'm quite confused if it's going to be A1 or it's going to be A3, but the format is the same as this one. Going up is positive for the product, going down is negative. Now, if you want to determine C sub 1 and C sub 2, the same thing, you will work your way. This time you will use, for C sub 1, you will use this. Okay? So that you will have the C sub 1 and C sub 2. Actually, there's no need for you to complete the second column if you have already here written the n plus 1 row. So let's say, for example, you have until A sub 2. So your n is 2. So you should have 3 rows here. You don't need to continue until 4, 5, 6. Your number of rows here depends on the n of the last coefficient in your characteristic equation. So if your last coefficient is A sub 2, this is your n, then you should have 3 rows. You should have 3 rows here in your route array. And then make sure, so route array requires that for the system to be stable, all of this should be positive and non-zero. If any is 0 or you have something that is negative, it will be now unstable. Okay, you do the testing only if the polynomial equation will have all the coefficients as positive. Okay, now I'll close this one. Okay, excuse class, I'll just keep one. Just a minute. Okay, that's our route array. So these are the equations we use in finding the other coefficients in our columns. And that's it. I placed here at the end of the slides the summary of formulas. that are very important for you to take note of. So for step response for a first order system, so responses for first order systems, you can also see this in the PDF copy in Canvas. So these are the response equations. So this is for step, this is for impulse, this is for sinusoidal, and this is for ramp. Okay, and this is the phase log for your sinusoidal response. The amplitude ratio for sinusoidal response is the same as this one. You just take away the A. You take away the A from the picture, that is already the amplitude ratio for your sinusoidal response. Now, for second order systems, of course, if you recall our discussion a few minutes ago, we need to know our zeta first so that you'll be able to determine the corresponding type of response. So for underdamped response, zeta is less than 1. This is your response equation if it's subjected to a step change in the input. Critically damped, your zeta is equal to 1. This is your response equation. Overdamped, it's zeta greater than 1. It's 1 minus this. So I just wrote it in here. It will not fit in here. So this is your response equation. This is for step input. For impulse input, this is your underdamped response. This is your critically damped response. And this is your overdamped response. Now, if it's sinusoidal, you only have one response equation. So no need to determine the zeta. Your amplitude ratio for this is the same as the way you considered it in first order system. Take away only the A. That's the amplitude ratio already for sinusoidal response. Your phase lag here, unlike the first order system, capped at 90 degrees, this one can be 180 degrees. Less than or equal to 180 degrees, or it's asymptotic to 180 degrees. Your amplitude ratio here is not capped to be less than 1, unlike in the first order system wherein your amplitude ratio is less than 1. This one could be greater than 1 for a second order system. Now there are terms related to the second order system. So these are the terms related to the response of the second order system. Overshoot is dependent on the zeta. So a measure of how much the response exceeds the ultimate value. The ultimate value meaning the new steady state value. That's the overshoot. So you only need the zeta, you get it. Your decay ratio is your overshoot that is squared. Okay, this is the ratio of your successive peaks if plotted for your response curve. Your rise time is the time required for the response to first reach its ultimate value. So the very first time, if you're going to plot your response, the very first time it crosses the ultimate value line. That's your rise time. The response time is the time required for the response to come to within plus minus 5% of its ultimate value and remain there. So it's either 95% or 105%. So it's a range of value for the response time. For the period of oscillation, this is very different than the T sub n. Now, this is where most of the errors in the quiz wherein this one was asked, I could see in your error. So the period of oscillation is really the time elapsed between peaks, or the time elapsed between alternate crossings of the line y equal to 1, if y equal to 1 is your ultimate response. Okay, that's it. But when you want to determine the natural response, it's 2 pi tau. It's different than this one. They're not the same. And you can see here that your period can solve for the tau. If you know the zeta, so you can solve for the tau. And your natural period of oscillation will be this one, the 2 pi tau. The period of the system when it oscillates continuously without attenuation. So this is very different because in your T sub n, This is your T sub n. Or rather, this is your T. There is attenuation. The peaks attenuate, it decreases. In the case of the T sub n class, it's this, but there is no attenuation. So the peaks does not die down and remain as after some time. So it oscillates, but there's no oscillation. There is no attenuation. There's no decrease in the value. Your period that is measured here is T sub n, not T. So the two are really very different. So you cannot use the T that you have and simply multiply it by, I don't know what you did, but the value of your T sub n is different, should be different than the value of the T. Okay? Even in the definition, they are two very different things. Okay? So there is no attenuation in the case, of the natural period of oscillation. Okay? And that ends our review for process control. What I have here in the next part of the slides are actually the problems that were given to you in the problem set. So every time, since we meet, our review is 3 hours, supposed to be every week. So I'll stop sharing now.